Okay, so on the Zoom, are you guys able to see the PowerPoint presentation mode? Okay. Okay, thank you. Okay, so we are going to talk about the diffusion model. So as I said that this course is on generative AI. Computer vision AI. Actually, the most important part of AI is computer vision. All the revolution is due to computer vision. Okay, so just keep in mind. So we talk about text, even though this ChatGPT large language model really convinced the public that AI is real, is going to make a huge impact, but it was after a lot of work, people working in different areas of AI. So large language model will generate or predict the next word. That's the beauty of it. It's so simple that you train the model, just predict the next word, and you don't need any supervision because you already have what should be the next word, and it works very well. So that's why it's called generative, generate a text. Okay, and other thing is it's autoregressive. So you predict one word, then that word you bring it back, and you put a second word, then predict the second word, and third word, fourth word. So it's called autoregressive. You are bringing it back. So only problem with that is that you are going through every word to predict. You are going through the whole feed-forward process. That's a lot of computation. Okay, because what is in the in these model is the attention. You have to compute the attention, and attention takes a lot of computation. Now, if you do the VIT, you just put an image and you get the encoding, and you can use that features. You can classify and so on. But it's just one feed-forward pass. But in the autoregressive, you are doing many, many passes for every word you do the pass. And that's why you have to do this attention there, and it's a lot of computation. So that's why the notion of caching the key value and queries comes in, and you can save those so that the next word prediction, most of the words you already seen, you already have computed those. You can use those. The next word you can compute, only one is changing. So that's one of the main thing. Contribution in DeepSeek R1 was that they came up with a very innovative way to do the caching, essentially doing the reduction, take a very long key and reduce a lower dimension, do the attention there, then you do the higher dimension. So this is due to autoregressive. If you don't do autoregressive, you don't need to do caching. Okay, so now in this course, we have been focusing on the large multimodal model, or LMM, or the VLM, and we have been building upon the LLM, and mostly it has been a lot of LLM, but very small part of the vision, just in terms of encoder, projector, and so on. Now, images, the first, image generation model by OpenAI was DALL-E. And DALL-E actually used autoregressive model, which converted the image in tokens, like words, and you do the autoregressive fashion. And it was pretty good. But now the diffusion models came in, which is not autoregressive, okay? And diffusion model, you can generate images and video, audio, and everything. So it's a very different. Now the thing is that there are two different ways. You can do the language, you can do the images, and images, because the continuous space, you have these numbers, right? Each token is 0 to 55, you have RGB and all this thing. but the words are discrete. So there's always a problem if you want to do autoregressive in images, you have to do quantization, which is called vector quantization. You take these continuous space and quantize in tokens, then you can treat like a language. And but now there are methods that you can do both in one transformer or one model. And actually, your friend here, Sabir, is working on a method where you can do the image generation, also language generation in the same model. So there's another pretty interesting direction which is happening in the transformer and also the state space model, which is called Mamba. So, so I'm going to talk about diffusion model, the basics of diffusion model. I know some of you already know this, because the thing with this class is some of the students are very experienced. They're doing research and PhD, and some other students, they just start. Yes.
Shut the fuck up.
Can you unmute, please? So some of the students, they are just taking this as second class in computer vision. So I want to be, fair to all those people. So that's why I covered the basics, even though for some it may be just, review. For example, here, Anirudh is submitting a paper using diffusion model to fix some of the problems in diffusion model as we talk about not safe for work and so on. So I'm going to, give you very general introduction on diffusion model, and some of this work, is taken from our survey paper we had in DDPM. And so I'll start with the motivation and high-level overview. In particular, we'll talk about diffusion, denoising diffusion probabilistic model, which is called DDPM, which is the first one. It's very popular. Then we'll talk about noise condition score network, or score matching, the different names. And then conditional generation. And if we have time, maybe talk about stochastic differential equation. So these are the three different methods, DDPM, the score network, and stochastic differential equation. All of these do the diffusion model, and all are actually related and are similar. You can start with one, arrive at a second one, and third one, and so on. So it's pretty interesting. And this probably material is very theoretical, needs a lot of math. So I'll cover, very high level. And of course, there are a lot of applications. So the very impressive thing about diffusion model is that there was a first paper in 2015, then there was nothing, then there was one or two paper in 1920, then all of a sudden 21, it just blew up, and 22, now this, is here, that, every paper has diffusion model these days, okay? So that is important and to notice. So, and there are lots of blogs and so on. I got some material from this blog. I think you should do it. Yes?
I was wondering if you could elaborate on the explanations for why it became popular after the original paper.
Because, it worked. It was able to generate these images which are so realistic, and it's very general. You can generate images, you can generate video and everything, and some mathematical, there's a lot of theory behind it. And
the original paper was not specific to vision, was it? Or they figured out?
Yeah. So that's so the main idea is that once people discover this can be used, then there's a lot of work went through. People explain and generate these different models and simplification and so on. So it is due to all that. Yeah.
Was there
Yeah, all these things are there, right? So neural networks, started into, 40 years ago, but people did not take it seriously because it was not right time. So all these things came, the data, the computation, and so on. We are going to talk about stable diffusion, which has made a big progress because of they did this latent diffusion. The image is very large data, so to do this diffusion model on the images, it takes a lot of computation. But they took the image and reduced a lower dimension, did diffusion on that, and then decode an image. So which is stable diffusion. Everybody knows these days to use. So now they are fundamentally different from other generative models, as we discussed, different from the predict the next token, gain, and so on. And so the idea is that you want to, decompose an image generation process in many small denoising steps. So like gain will generate, just one shot, generate an image. Of course, it can improve comparing with the real image and discriminator and adversarial part. But this process of diffusion model is very different, and it is will taking small steps. At the end, it will end up with the image. And then in a way, it will correct itself, gradually produce a good sample, and I'll show you. So in the beginning, they were very slow compared to gains. But now, they are competing with gains. People don't really use gain that much. So, so the basic idea, and that's a good thing about the science. Once you figure it out, it's very simple, very intuitive. So basic idea is very, very simple. You take an image and you keep adding noise until it becomes complete noise. Okay, and then that noise will have a distribution, Gaussian distribution or normal distribution, and this process is called forward process. Take an image, add noise, add noise, add noise, and so on. Complete noise. You just destroy the whole image. And then you train a neural network, which will learn how to denoise an image. You take a noise image, it'll give you remove noise. So that is the learning process coming. So all these things you're learning in AI, you'll have to have learning. And that's why it's making difference, right? So this was a big breakthrough that we can learn the process of denoising. And so the idea is then, if you learn network input to the noise and output denoise image, then you can start completing noise, and you keep denoising. You start with nothing, complete noise. You cannot figure it out, but you denoise, becomes emerge image, which is amazing, right? That's the idea. So, so this is called reverse process, and this model is able to, this process model the reverse process. This being able to model the reverse process, and we can generate the data. Okay, so there are a lot of applications in diffusion model: image generation, text to image, super resolution, image editing, inpainting, image segmentation, and so on. So I'll quickly show you. These are synthetic images. It's amazing. You can see high resolution images from different data set, Elson, more images. All these things. You can inpaint. You can remove part of the image and inpaint with, again, these are realistic images. In colorization, you can take black and white image and colorize it. You can do that, with that time when this President Lincoln, Abraham Lincoln, wasn't there. There was no color camera, I assume. You can now have a color picture. He looks like this. So stable diffusion, as I say, that was a big breakthrough, this paper, and we are going to discuss in detail in this paper also. So, so that can generate text image, given this street sign that, reads latent diffusion, because there's latent diffusion there model, can generate image like this, and Picasso, and things like that. So, and also you can actually give windows, identify you want to put a cabinet here, you want to put a shelf, a floor, and generate image like that, which is pretty impressive, and so on. So then there was this paper, got actually best paper award in CVPR, I think, Dream Booth from Google. So you take, train model, because these models are trained on a very large data set, like Lion, 5 billion, right? So, but now you want to specialize the model for your images. So you take these 4 images, and then you want to put this dog into Acropolis and doghouse and sleeping. So this is called a dream booth. So very quickly you can get a same dog present here, taking a haircut, and put images. You can put these glasses and put a prompt, and you can do that. And you can take 3, 4 images, and you can put this your backpack, backpack with a night sky, backpack in the water, and so on. So lots of very interesting things, and so on. You can have different colors of this thing. Okay, so input is this. Now you want to generate these images of this car, purple color, red color, yellow, blue, and so on. So very impressive. And also, of course, these video generation. This is looks so realistic. You can generate these kind of videos, okay, and these kind of videos from Google. So actually, every day on Twitter, this guy and this guy, they have so many examples of very synthetic videos, very good looking and realistic looking videos. So all these, basic principles we are going to discuss how this works, okay? So, high level overview, as I said, diffusion model is a probabilistic model used for image generation. Then was process of gradually degrading data, and that's where you have to now use some math. So we are going to use the distribution, probability distribution function, okay, probability density function. So, so you guys know the distribution. You learned from statistics class, right? So if I take the height of people in the class, some are tall, some are short. So maybe we have 2 modes. This is a distribution, and the random variable is a height, just one scalar. So I can take all these and make a distribution. Okay, I can collect all the people and have the distribution, and that distribution play a very important role in the diffusion model. Now we have images. So images have lots of numbers. So suppose if a 100 by 100 image be 10,000 pixels, so it will be a 10,000 dimensional vector. So that distribution will be in 10,000 dimensional space. As compared here, it's a distribution 1 dimension, height. But the notion is the same, okay? So we have a data distribution, like we have imaginary data set, we have a straight up distribution. So we take all the images, training, and we convert it into a vector, and we can find a distribution. So what we are going to do is take a sample from, say, 1 image, and we'll add noise, keep adding noise, keep it, until it becomes completely noise. And that noise is modeled by Gaussian distribution or normal distribution, and it looks like this. So that is called the forward process, okay? And of course, when it's a 10,000 dimensional feature vector, 10,000 dimensional vector for distribution, we will have the mean vector and covariance matrix. Yes? 10,000 by 10,000 covariance matrix and 10,000 dimensional mean vector. And they will play a part. So then the reverse process is we will sample a vector from the Gaussian distribution, which is a complete noise. Then we will denoise, denoise, denoise. And it will become a sample, which will look like an image. Here it will look like garbage. Okay? So that's the magic. So, so as I said, there are three categories of this. The DDPM and NCSN, score networks, and the stochastic differential equation. So we'll focus today on denoising diffusion probabilistic model. So these are notations. So data distribution, like imaginary data set, is distribution when I showed you left side. We'll call a QX, Q of X, okay? And any distribution will have the random variable or random vector and mean vector and the covariance matrix. So this is the notation for Gaussian distribution and normal distribution. This is our vector, random vector, this is the mean, this is the covariance, and this identity matrix. So we are assuming that the standard deviation or variance is only on the diagonal. So this independent distribution. The first element of this vector doesn't depend on second one and third one, just to simplify. So now this is a random variable, which is image, and this mean vector, this is covariance matrix. And so now any distribution we want to generate a sample from that. So easy way to generate a sample is that we take the mean vector and take the variance and generate a random random vector from the zero mean and identity normal distribution. Okay? So in the original, any distribution, we'll start with the data set. It will have some mean vector and some covariance matrix. But here, N zero means zero mean and identity. So we will randomly sample a vector from this distribution, and you can do in your code like rand, it will give you a random vector in any distribution, uniform, Gaussian, and so on. So we take that vector and take the mean and put the variance, and there'll be a sample from that distribution. Okay? So now forward process is take an image. Now this x0 is a sample from the original data distribution, like imaginary distribution, all these images. So this is one of the sample. So we add noise. This is like x1, x2, x3, x4, and this is like xt, uppercase T. And such that now this will become the normal distribution with zero mean identity matrix, complete noise. It's also called white noise. So we started with Q of X, now we ended up N0I. Okay? And so the reverse process, we will take a sample from the Gaussian distribution, zero mean and identity covariance matrix, denoise, become a sample. That's it, very intuitive, very nice. So that's what we are going to do. Now the thing is, when we, the forward process, we are going to take the, since we are going to take x0, put noise, get x1, then we'll put a noise to the x1, get x2, put a noise to x2, s3, and so on. So it's a sequence. So therefore, we will model this a conditional probability distribution. Probability of xt given xt minus 1. Okay? So that again will be a normal distribution with this mean and this covariance matrix. And these are beta t is small number less than 1. And this iteration from 1 to t. So if we want to generate a sample from this conditional distribution, and this is the way it will be. We'll take the xt minus 1, and this is again noise, and we add that and get xt. If we are given from this distribution, this would be a sample from that. So now the question is, so at the end, it is replaced, image is replaced by the noise. And so now if we have x0, how do we get to xt, right? We are doing that, and one will be, we will take x0, get x1, x1, x2, x3, x4, we keep doing, and these are the probability, conditional probability distribution. We will multiply all those. We will get this probability x0 given, xt given x0. So there are lots of, products, multiplication of these. But that's an indirect process, right? So the question is that can we go directly in one shot, which is called the ancestral sampling. So what we want to do, we want to go to x0 to xt. We don't have to go through these different steps. So we can, this is called a reparameterization trick, because all these are distribution, all are there Gaussians. So let's say this is xt. If you know the xt minus 1, we can generate xt like this. Okay? Now we can use the same formula. Given xt minus 1, we can generate xt minus 2. Right? We just replace here. T minus 1 with t minus 2. So, which will be like this. Then take the xt minus 2, we can generate xt minus 3. We can keep extending this, xt minus 2 and xt minus 3, xt minus 3, xt minus 4. We keep growing that, then we can show that xt can be expressed in x0. And you should do this at home, actually. Okay? And that is the reparameterization. Of course, these parameters, are changing because we are keep multiplying these different beta and alphas and so on. So that's the idea, that every time we have this noise, they are under Gaussian, and alpha t bar is a product of alpha s, and s goes from 0 to t, and alpha t is 1 minus beta t. Okay? So now we have your xt can be sampled directly from this distribution using this. So then the main question now is this, like a theory and how it should work and all this thing. Now the question is that how do we train this? Okay, how do we denoise so that we can, then synthesize a generated image? Okay, so as we talk about that, the forward process is modeled by Q, xt minus 1 to xt, x0 to x1, x1 to x2, and so on. And reverse process is modeled by p theta. So p theta is what we want to learn. We want to learn how we can estimate this probability, which can go from xt to xt minus 1, reverse process. Okay? And this is called reverse diffusion process. So what it means that, well, this is the distribution, and what we need to know, we need to estimate the mean vector of the distribution, and we need to estimate the covariance metric of the distribution. Then we have the distribution, and we can then sample from the distribution, and we can basically denoise the process. Okay? So whenever you see theta, which means there's a learning, the parameters of the network which will learn are theta. So you want to determine the theta. So, so that's what we are going to do. So we want to essentially approximate this, the process of q xt to xt minus 1 by theta. And theta is the neural network which we are going to learn. So now we can approximate both. We can learn mean and the covariance, or we can, and these will be the theta, will be the parameter of network, or we can actually fix the variance and we can just predict the mean. And you can do that also. It will simplify. So now all this thing you can do what is called the U-network, U-net neural network, U-net, okay? So it has encoder and decoder, and so we will put in a noisy image, and we want to get, and we put a time, this is xt, which time we have this noise, and then T is condition, and we will get the output of the theta, the parameter of theta, which is the mean of this. And then once we have theta, we have this distribution, we can sample from the distribution. So now U-net is a network which is very important to understand, and that's where it started, the diffusion model. And this looks like a U, that's why I call U-net, right? So, so in this one, and this was a paper actually, the rumor is that this paper was first submitted to CVPR and got rejected. And famous author Brox in Germany, actually, I visited his lab also. But then they submitted to the medical imaging conference called MICAI and got accepted. Right now it's 100,000 citations, okay? 100,000. So this was a breakthrough. So
did you say 100,000?
Yes, 100,000. 100,914 here.
Wow.
Can you believe that?
I will check it. That's a big number.
Yeah. Okay. So now let's try to understand this 100,000, paper. So U-net, okay? So what we are going to do, we will use this notation. This is if the arrow is this way, blue is a convolution, 3x3 convolution with ReLU. If the black one is a copy and crop. If the red one go down, we will do the max pooling, reduce dimension. If the green one going up is 2x2, will be up. And this is the 1x1. Okay? So we started. They did on the medical imaging, which is a black and white image, just one channel. So the image was 572 by 572. Then we did the 3x3 convolution, ReLU, 64 channels. We did one more, 64 channels. So this is one. Then we went down and reduced downsample to the half and become 248. 248, let me see, 284, okay? So we get, again, 3 channels, and now the number of channels is 128, 128. Then we did further 140, and there are 256 channels, 256 channels, okay? And then we reduce more to 68 from 138, 36, I think, and then increase. We are keeping increasing channels and reducing the dimension. 512, 512, then reduce further 32, and then we will increase the channels to 10, 24, again the same dimension 28, and then we now going to go up 2x2 convolution. From 28 we'll go to 54. Then here is a new thing, which is skip connection. So we'll bring in the half of these and half from here, and we'll make it this one, 1024, okay? And then we will have another convolution from 1024, we'll go to 512, and then we'll do upscaling, and we will again do the skip connection. We'll take half of this and half of this, 512 and 512, and then 1024, and keep going like this, keep going like this. And this is, sorry. So that's it. So at the end, we will get these two dimension output segmentation map, and this was used for medical imaging, and they found out that you can actually do the cell tracking and cell segmentation. Given the image like this, you can do like this, like this. And they got actually another conference in medical imaging called ISBI. ISBI is a conference, and Rizwan has a paper this year on this. So they got results from second base for 46%. They got 77%. So that's why 100,000 citations, right? People look at this, 46 to 77. You kill everybody, right? And that's the way this became very popular. It works really good. Okay? So now we are going to use the UNet to train the denoising process. And denoising process will give us, this network will give us a mean of this distribution. And once you have mean, we can generate a sample, right? So whenever you have a network, you need to train. And the question is, how do you train? What is the loss function of training? So you have, from physics, entropy. So you have two distribution. You have a distribution P. Entropy of distribution is P I log of P. You multiply, it gives you entropy of distribution. It gives you disorder, right? So if there's more disorder, then more entropy. And if there's more entropy, then more information. You need to represent more bits. So entropy. But what you are more general is called KL divergence, which is the distance between two distributions. This entropy is just one distribution P. So if you have two distributions, distribution P and distribution Q, you want to find how similar they are. So that's called KL divergence. And essentially, you find the entropy P and Q and P and P. So this is the P and log P and P and log Q. So this is this difference from P to Q. This is not symmetric. Q to P will be different. So this is saying how different Q is from P, and this is the way to compute. Now, you are familiar with cross entropy. That's what you have learned in 5415, how to train a classifier, right? So cross entropy will just take this one part, which is the log P multiplied by log Q, okay? So this is your cross entropy, and is looking at, because when you look at first part, P and log P, it does not tell you anything about, it tells you only thing about P. But in the training a network, you are looking at the distribution of what network is predicting, let's say P, and the distribution what the ground truth is. You're comparing these two distributions, and that's where you would use a cross entropy. So therefore, this is more meaningful, and that's why we use the cross entropy. I mean, some people use KL divergence also, but it doesn't make a difference. So cross entropy is important. So it's a basic idea that why do you use cross entropy to train the network classifier, and this is the reason. Okay, so now we are going to use this notion of this KL divergence to train this denoising network. Okay, so this will be the training objective, And so what we are going to do as we talk about, Q is the original distribution where we got this data distribution, we sample those and we noise starting from x0, x1 and so on. And P theta is the distribution, the network we are going to train which will learn this distribution. So we want these two distributions to be similar. We want to minimize the distance between two distributions, and KL divergence is the measure which you're going to use. Okay, so one is a true probability of the forward process when condition of origin image. So and now remember here we're starting t is equal to 2. So which means that this will become the x0, 2, and x1. So because x0 we started, so given x1 we want to compute x2, and given x3 we want to compute x4 and so on. So other way, given x3 we want to compute x2, given x4 we want to compute x3 and so on, because we are going backward. So now in this one we have the x0 to xt, and this is the term because we can ignore this because we already know the p theta where we start is the normal distribution 0 to 1, because that's where we start. The xt, we started with xt sampler from Gaussian distribution. We keep denoising until it becomes sample. So this we already know, and we don't have to use this term to train the theta network. So we can ignore that. And this kind of finishes now that we have 2 to t, and we have the last term here, because here we will have t minus 1, the maximum. So then this is the other term, which is like a reconstruction error. So given x1, we want to be able to compute the x0. So now we'll go in detail about this. And so the first term, this one is a reconstruction error. So we want to, given x1, we want to compute x0. Given xt, we want to compute xt minus 1, xt minus 1, xt minus 2. Keep going until we receive x0. So this is reconstruction now. But the probability distribution is we want to make sure that this p theta is computing very similar to the q. And now another interesting thing, that because this whole formalism is a Gaussian distribution, and that's where it very simplifies, right? So now if you take the KL divergence of two distribution, and this is defined for any distribution, uniform, Poisson, and all kinds of distribution. There are many alpha, beta distribution and so on. But this is true, all of this is true for Gaussian distribution. Now, good thing is the KL divergence for Gaussian distribution is very simple. You just subtract the means. You take the mean of this distribution, mean of this distribution, subtract. And very interesting, and you can show that actually. So that will help us. And on the top of it, we are going to introduce some simplification that will actually make this whole thing very simple. So now we are going to start notation here. So the conditional probability xt of xt minus 1 given xt is again a Gaussian distribution. This is a mean, this is a covariance matrix. And these are the constant defined, as we discussed before. And now the mean vector is given by this. So we sample the noise from the 0, mean, and identity matrix, normal distribution. We plug in here, and we have these alpha, beta, and all this thing. We get the mu tilde for this conditional probability distribution, the mean of that. And this is identity matrix, and this is a constant beta t, which is defined like this here. So now when we do that, now we can actually look at the mu theta, the mean of the theta p theta distribution. This was the mean of the Q distribution because we want to make these two distributions similar. Okay? We want to minimize the distance, the loss function. So therefore, we can take the same idea. So instead of zt, we put a z theta. Zt is, we will add the noise, but z theta, it will predict the noise. We'll put a xt as input, time as input, and it'll predict the noise, which should be similar to zt. So when we subtract these means, then becomes very simple. That zt is the input, which we add the noise, and z theta, it should predict, it should be very similar. We want to minimize these two. And that's it. So, and this is a constant, and all this we can ignore. So therefore, to train the unit for the diffusion model, we are going to use this loss function. We will take each sample x0 from the original distribution, like the ImageNet. We will take zt from the normal distribution, and we will do this iteration from t is equal 1 to t, and we'll go through all that. And that's that function, objective function called L simple. It simplifies a lot of things, and it's very intuitive, that we are basically estimating the means of these distribution. So training algorithm becomes at the end very simple. So we take the image from the original data distribution, call it x0, and we sample the t from random for the normal, for the uniform distribution, and then zt from the normal distribution, and then from there we get xt. We take the x0 and we can get the xt using this one-shot algorithm, as I told you, reparameterization trick. Like that, we can compute xt from any x0 like this. And then now xt is here, and we will learn the theta by minimizing this error. So we initialize theta with some initial parameter and put in xt here and differentiate this, get a gradient, and put the learning rate, and iteratively we compute these theta, and that's it. So that is the unit, training of unit for diffusion model. Okay, so the main idea is that two distribution, from the data distribution, other is the normal distribution, and we have noise, and it is going to give us denoising image, and we can use that. Okay, so if you go in a little bit detail, so we sample an image from our data, then we choose a random step of step t for forward process, then we sample noise zt from normal distribution. We get a noisy image because we want to take the original image and add the noise at different time steps. And then we update the neural network theta parameters, minimizing this error. And that's it. Okay? So therefore, this is our unit. We take an image here, we get a time here, we come out z theta because that's what we have trained, and then we can put that in the normal distribution, and z theta goes here, and this is u theta, and then from there we can actually sample an image which looks like that. So once this is trained, so this is the sampling process that we are going to, again generate random vector from normal distribution, and we will take the z from there, and then we will add this E theta and Z here. E theta we are getting from our network which we have trained, and we return, and that will become sample. So that's, I think, what I have here. And as you see that at the end, this works pretty well, and you can, train this if you have learned how to train a neural network. But there's a lot of math involved. But the main point is that understand the basics, that any network you want to train, what's a loss function, and this is a loss function, and then what goes in to the network, and how do you actually train this, and once it's trained, then how do you actually sample an image, which is shown here. Okay, so please look at this carefully. We will put the video and also the PDF. But if you can understand this intuitively first, then at least have the idea of the unit, then I think you should be able to do pretty well in such images. But it does require that you need to understand the notion of distribution, the conditional probability, the Gaussian distribution, and KL divergence, and all this thing. And I've tried to give you a flavor. There is a lot of background which you can actually cover yourself later. Are there any questions from here? Yes.
So when we're doing the denoising,
Yeah.
how do we steer it to what we want to generate?
No, so that's the whole idea, right? So this network has learned, given the noisy image, it will denoise. So now it has learned, so we have taken an image and noise and predict. Taken an image, there are a lot of training data, right? So it has learned. So when we do the inference, we sample a noise, and we input a noise image, and it denoise. Now, since we are randomly sampling noise, it can be anywhere, right? It doesn't necessarily will be the same image which we started in training, it went through, So there are lots of many random possibilities, right? So we start a random vector, a random image, denoise, it becomes the real, one of the image which can belong to that distribution. It's approximation. And that image is a synthetic, and it looks real, but it's not exactly same. So you are not, the reason you want to steer it, because it has learned. It has learned many examples. Take this sample, just do that. Take this one, let's do that data set. So the image you will generate will be from that data set. It has learned. Now, if you want to generate the image from other data set, then you have to fine tune. Or if you train it on very huge data set, like 5 billion, so it will generate any kind of images. So that's the way kind of it works.
Right, but like if we're generating a picture of a cat,
Yeah.
a picture of a dog, from the random noise we start, when we were training, did we encode like a caption into the image?
Yeah. So that we are going to talk about on Wednesday. So right now we are talking unconditional image generation. We take a data set ImageNet, for example, we can generate all the images from that data set, but it can be any class, 1,000 classes. But now tomorrow, Wednesday, we're going to talk about the conditional image generation, that we want to generate an image from a particular class, or we want to generate an image from a caption. So we are going to talk about that. That'll be another condition. Okay? Yes?
Can we encode like authenticity features or such that
Encode what?
authenticity, like for instance, we can encode
Yeah. So, yeah, so I think there are lots of issues related to these image generation. So one is that, how do we know that is a real or the generated image, right? So you can, a watermark is, you can have a separate technique. Once you generate an image, then you can go through the watermarking and you put a watermark and you put that, and people are doing that, right? So that's fine. But the more interesting thing is that scientific problem is that given an image, can you determine if it's a real or the generated image? So there's whole research in that area. The other topic is that is the generated image exact copy of the training image? That's another big issue, right? So, these things, people are working on. Yeah, it's a research problems. Okay, any other question?
Dr. Shah,
Yeah.
Is the diffusion implicitly a recurrence model? Like, we can say that it's Markovian in nature, right? Based on the previous step, you're predicting a noise for the next step. So if it is implicit, if it is Markovian, is it also implicitly recurrent? Like, does it show implicit recurrence? If it is implicitly recurrent, then what is the state in the diffusion model? Like, how can we define state?
Scale?
State.
How can you define scale? Or,
State.
state, okay. Yeah. So you are right, it's a Markovian. So, as we say, this conditional probability just depends on the previous one, right? So, so there's no, directly, we don't have to bring in the, notion of the states, but see, the main thing is that as we discuss that there are different, we are doing in a way, let me look at this formula here. So we have the conditional probability, I think there was a formula here. The products. So if you look at okay, here. So see that you can look at that as a joint probability, right? So we have x0, x1, x3, x4, up to xt. So this is the joint probability in these so many, depending on how big is t. So if it's 500, so it will be a joint probability of 500 dimension. So that is impossible because even though, it is recurrent, but we are depending on the previous one. So what we are doing here is Markovian assumption, as you mentioned, that the xt minus 1, xt depend on only xt minus 1. And x1 depends on only, x0. So we are simplifying as compared to putting all those, variables, and this works for this particular assumption of Gaussian distribution and so on. There are a lot of equations. So the Markovian process, you have the different random variable and their states, but the assumption Markovian is that depends on only one in the previous one. It doesn't depend on the other ones. Is that what you are asking?
Yeah, I was just confused. Like, if it seems like diffusion is implicitly recurrent.
Yeah.
It kind of has a recurrence relationship, but I was confused. How do we define state in such a process?
It's not necessarily defined states. So, just look at the probability distribution. If it is a probability distribution of the, many random variables, so it's a joint distribution, depends on lots of things. What we have simplified is it depend on the only previous one. And that makes it simple. Otherwise, it will become very complicated. And the Gaussian lets you do that. Okay, so we will end it here. So.